So hello, everybody. My name is Willie Turchetta, and this is my paper, Understanding Slowdown in Large-Scale Heterogeneous Systems, that I wrote with Kristen Gardner, my professor last year when I was a senior at Amherst College. This was actually my senior thesis that has since been adapted into a paper with very much the help of her. So the way that I'm going to go about this is I'll first talk about the model that we were working in, then go into a little bit of the problems that we're actually trying to solve, talk about what slowdown actually is, some of the mathematical analysis that we did, and then talk about the numerical results derived from that analysis, and then talk a little bit about where this project is going. That's going to do. So we were working in a heterogeneous system, and basically all that means is that we just have a bunch of servers running at different speeds, some dispatcher. We call the number of servers in the system K, and we say that arrivals follow a Poisson process with rate lambda K. So lambda effectively can range anywhere from 0 to 1 to keep stability. And we'll say that jobs follow an exponential distribution with parameter 1. We'll say that there are server speed classes. And so what this means is if every server is running at the exact same speed, then we'll call R1. And if everyone's running at a different speed, we'll call R will be K. So it ranges from 1 to K. And we'll call each the proportion of servers in each given server class Q sub I. So if we have 1,000 servers, 500 are running at one speed, 500 running at the other, R would be 2, Q sub 1 would be 0.5, and Q sub 2 would be 0.5. Also, in this model, we'll be running processor sharing for most of our analysis and results. So the problem statements. So the first is how should we actually go about defining slowdown in a heterogeneous system? And then the other is, can we design dispatching policies that perform well with respect to slowdown? So now I'll talk a little bit about what slowdown actually is. It comes from a metric, actually mean response time, which is a well more studied metric. But slowdown has an element of fairness to it, where basically you divide it by the size of the job. And what this does for you is it allows you to have some metric of fairness in which, like, say you're down, you should be larger jobs should be okay, taking longer to be processed than smaller jobs. So I mean, this is like you're downloading a movie, you should be okay with it taking longer than if you're just downloading a single PDF. So yeah, the intrinsic definition of slowdown is just the response time over the size. It's been shown in processor sharing in MG1 that it's just 1 over 1 minus rho is your expected slowdown. Previous attempts have been made to define slowdown in a heterogeneous system, and the way people have done it is response time over the size over the capacity of the system. And this is good because it can let you like compare different system configurations against each other. But an issue is that when you start to have your capacity increases, your slowdown will always increase just because your capacity is increasing. And you start to lose the nice like meaning of what slowdown actually is. Because generally speaking, if slowdown is 1, that means that a job just like ran in isolation. So our definition adapts this to just say it's the response time at a given server over the size of the job. And then we finally will say that the expected slowdown is 1 over 1 minus the load time multiplied by the speed of the server. And yeah, so some benefits of ours are that you can now compare it across systems. The capacity doesn't matter, isn't taken into account anymore. So you can compare different systems configurations more easily. The only drawback to ours is now you can have slowdowns less than 1, which kind of makes sense though, because if you're running a job in isolation on one server, and you have a slowdown of 1, and then you run the same job in isolation on a server running twice the speed, your slowdown really should be less than 1. Getting into what the dispatching policy that we studied this under is something we actually adapted called p-SITA, which comes from SITA, which is size interval task assignment. Basically, we have our exponential distribution, job sizes on the left, and we can split jobs into small jobs and big jobs, and have an independent dispatching policy for each. So what we can say is then when a small job comes to the dispatcher with some probability, we can send it to the fast servers, and then it'll be uniformly distributed among the fast servers from there. And then with some other probability, we send to slow servers, and it'll be uniformly distributed among from there. And then when a big job comes in, we can have a different set of probabilities to send to the fast servers and send to the slow servers. So overall, our dispatching policy looks something like this. where we have some set of probabilities to send the small jobs to fast servers and slow servers, and then a unique set to send the big jobs to fast servers and to slow servers. So we did a little bit of analysis, and basically this is what we came to for our expected slowdown in the system. The boxes in red are parameters where we can tune knobs in order to change. So looking at p-SITA, there are a few knobs you can turn. You can change where the size cutoff is, or you can change that set of probabilities for big jobs and small jobs. So the ones boxed in red are ones where tuning our parameters will actually matter for those. So now looking at our optimization, again, the boxes in red are the ones that'll be changed, and the boxes in blue now are ones where like the top one where it's x sub j plus 1, that's your size cutoff, and p sub j sub I becomes your probability that you send a certain size job to a certain class server. So those are again, the knobs that you can turn in order to be able to affect this. It is a little bit of a weird optimization problem in the fact that it's not convex. So you do have to do kind of a brute force to solve this optimization problem. But when we did this, we found this. So this is our system with two server speed classes, and half the servers being in one server speed class and half of them being the other. We found some interesting things. First is that as the arrival rate increases, that it just kind of becomes SITA, size interval task assignment, where you're basically saying all the small jobs to all the fast servers and all the big jobs to all the slow servers. And this makes sense because if you're sending all the small jobs to all the fast servers, you can churn through more small jobs quickly, and so you'll bring that slowdown down more. And so as you're going across these like lower loads, all you're changing is your size cutoff, what you're classifying as a big job and what you're classifying as a small job, and you're basically just decreasing what it means to be a small job as your arrival rate increases. Something interesting happens where at larger arrival rates, you do start to have this the third knob starts to become nice to turn, where you can now send some of the big jobs fast servers. And this is just because you end up actually clogging up the slow servers because they can't process that many big jobs. And yeah, so then the other thing we looked at is we tried to compare slowdown to mean response time. And here we have two charts, where the one on the left is a chart where both have expected slowdown on the x-axis and mean response time on the y-axis. And then we have the probability on the left, we have the probability that we're sending a big job to fast server, and the one on the right is the probability we're sending a small job to a fast server. And basically what we find is that expected slowdown and mean response time, they are directly related, like making in group, or if one gets worse, the other will also likely get worse. And that makes sense because they both have some qualification of how long a job is waiting at a server. But they're not exactly the same thing. That's what these curves kind of show us, is that as your arrival rate increases, the optimal policies start to differ by more and more. So you start to need to make a bigger decision between whether or not you want to optimize for slowdown or response time, or if you want to be somewhere in between the two. So that is a little bit about it. Just wrapping up here, our contributions were defining slowdown in a heterogeneous system, the analysis of a new dispatching policy, p-SITA, an extension of SITA, and then just looking at some trade-offs between mean response time and slowdown and the differences between the two. So for future work, the first next step would just to be continue under the same framework and just do more numerical analysis with more server speed classes and more job size cutoffs. We did do a little bit of work in increasing the job size cutoffs and found that there wasn't much of an improvement to slowdown. But our mathematical analysis is generalized, so you could do it fairly easily. And then just expanding our metric of slowdown to other scheduling and dispatching policies. So maybe analyzing slowdown under round robin, or I don't know, some other form. So with that, thank you. I appreciate everyone's time. And yeah, does anyone have any questions?